And next, now we'll discuss the shunt generator in just a second. So in shunt motors, this is the circuit diagram for shunt motor. So here you are having this is a supply voltage which we are giving to the armature, and the shunt field winding is directly connected across the armature circuit. Okay, and therefore now this terminal is supplying the line current IL. So here IL is called line current, and IA is the armature current, and ISH we can consider it as a shunt field winding. Okay, current to the shunt field winding. And here the resistance of the shunt field winding is always higher than the armature winding. And next, this is because the shunt field winding is having a large number of turns, okay, as compared to the armature winding. Okay. And next, so in this shunt motor, the field current ISH, the field current is always maintained constant. ISH is always constant because this ISH is equal to the terminal voltage V divided by RSH. So this terminal voltage is always constant, and your shunt field winding is also constant, and therefore ISH is always constant. And hence the flux produced is also constant in DC shunt motors. Okay, and here the net flux phi which is developed is always proportional to the ISH. The flux which is developed in a shunt motor is proportional to the shunt field current, and therefore this machine is called as a constant flux motors. The DC motors are called as the constant flux motors. Okay, and what is the voltage and current relationships for this DC motor? The voltage, terminal voltage, which we are giving it as a V is equal to. So whenever the armature is carrying a current, okay, and your shunt field winding is also carrying the current, then EMF is induced because of this force is developed by the armature, and the armature is rotating in the magnetic field in the effect of the magnetic field. So an EMF is induced in this, and this induced EMF is known as the back EMF. Okay, so this back EMF V is equal to the back EMF EB plus the current passing through the circuit, which is IA, RA, plus brush voltage drop, which we have discussed earlier. And here the line current IL. The line current IL is equal to IA plus ISH. Okay, and here ISH is equal to the terminal voltage V divided by RSH. So these are the voltage and current relationships for the DC shunt motor. Okay, is it clear? Any doubts?
Yes, sir.
Yeah.
Yes.
Next, we'll say the DC series motor. So the circuit diagram for series motor is here. The series field winding is connected in series with the armature circuit. The series field winding is connected in series with the armature, and the armature series field winding carries the line current. Okay, so the line current IL and V is the supply voltage. This is nothing but your supply voltage. Okay, and here so the schematic diagram. Now in DC series motors, the armature and field windings are connected in series with each other, and the resistance of the series field winding is much smaller than the armature resistance. So here the series field winding resistance RSE is lesser. RSE is less than the armature resistance RA. Okay, and therefore here the flux produced is proportional to the field current. But in series motors, the field current is same as the armature current, and therefore the flux is proportional to IA. So here we know that the line current IL is equal to IA. Okay, and flux which is developed phi is nothing but phi SE. Phi is proportional to ISE. Okay, and what is the terminal voltage equation for the series motor now? IL is equal to IA, and the terminal voltage equation V is equal to EB. It is a back EMF which is developed here in the armature circuit. EB okay, plus IA RA, the resistance drop in the armature circuit, plus IA RSC plus some voltage drop across the brushes, B brush. Okay, and for this machine, so therefore this will be equal to EB plus IA into the equivalent resistance RA plus RSC plus the voltage across the brushes. So this is the terminal voltage equation for the series motor. Okay, and the flux which is developed by the series motor is proportional to the armature current, or the current passing through the series field winding. Okay, in previous case for the shunt motor, this flux was constant, but in DC series motors, the flux is not constant. This is varies with respect to the load current. Okay, and now here the armature current and hence field current ISC will be the dependent on the load. ISE will be the dependent on the load. So in DC motors, the flux does not remains constant. This is varies with respect to the load. Okay, and now coming to the DC compound motors. So the compound motors are of two types. Okay, one is long shunt motor and short shunt motors. So we will discuss about the compound motors in detail. So let us assume that this is a long shunt compound motor, and the circuit diagram for the long shunt compound motor is given like this. So in long shunt motor, our shunt field winding is connected across the armature circuit and the series field winding. Okay, so it is a combination of armature as well as series field winding, and the current passing through the series field winding is ISC, and the current which is passing through the shunt field winding is ISH, and I total, or I can assume this as a line current IL, and this is my supply voltage V. Okay, and the supply voltage is V. Okay, this is a long shunt compound generator, and now coming to the short shunt compound motor. Compound motor. So here also, this circuit consisting of both series field winding and shunt field winding, but the shunt field winding is connected across only the armature circuit. Okay, and the series field winding is connected in series with the load. Okay, so this is your V across the, sorry, this is connected in series with the supply, not across the load. Okay, so series field winding is connected in series with the supply. Okay. Next, again, this long shunt and short shunt motors are further classified as the cumulative compounded motors and differentially compounded motors. Okay, in cumulatively compounded motors, the flux which is developed will be additive. Okay, so that is a pi SH plus pi SE. Okay, and in differentially compounded motors, this is the difference of these two fluxes, and therefore the net flux will be gets reduced. Is it clear? Any doubt on this?
No, sir.
No.
Clear.
No. Now we will write the terminal voltage equations for this. Okay. So for the long shunt motors, just you see that the line current here, I can consider this as a line current IL. Okay. So here IL is equal to IA plus ISH. Okay, this is the current which is passing through the long shunt generators, and we'll also have the current ISC is equal to IA. ISC, this one, ISC is equal to IA. Okay, and therefore now your terminal voltage are, and I need to find ISH here. ISH is equal to this shunt field winding is directly connected across the supply terminals. Just you consider this as a V instead of E. Just you consider this as V. Okay, this is the supply voltage. So ISH is equal to V divided by RSH. V divided by RSH, and our terminal voltage V is equal to. So now we need to apply KVL for this loop. Okay, so KVL for this outer loop like this, and therefore your applied voltage E is equal to, there is a back EMF in the motor EB. Okay, so V is equal to EB plus the current which is passing through the armature is RA, and the same current is passing through the series field winding also, and therefore V is equal to EB plus IARA plus the voltage drop across the brush, V brush. This is our terminal voltage equation for the long shunt compound motor. Okay, and these are the other current relationships for long shunt compound motor. Okay, and next, short shunt compound motor. So for short shunt compound motor, again the current passing through series field winding ISC, which is equal to IL. Current passing through the series field winding is IL. Okay, and at node A, let us assume at node A, ACL, I will write ACL at node A. As per this, your line current IL is equal to IA plus ISH. KCL at node A is nothing but IA. IL is equal to IA plus ISH. Okay, and now what is the terminal voltage equation now? I need to consider here again. This is nothing but the V. The terminal voltage is V. Okay, so or this is the supply voltage. V is nothing but the V is the supply voltage. So we need to again write the KVL for this loop. Okay, outer loop. This is your closed circuit. So for this closed circuit, I need to write the Kirchhoff's voltage. I need to apply this, and therefore your terminal voltage V is equal to, and in the motor there is a back EMF EB. So V is equal to EB plus the current passing through the armature is IA RA plus the current through the series field winding is IL, because ISC is flowing and ISC is equal to IL, and therefore IL into RSA plus the voltage drop across the brush. So this is my terminal voltage equation for the short shunt generator. So short shunt compound motor. Okay, and again I need to find out one more current here because I need to find the current passing through the shunt field winding. This one. So this current I need to find out. Okay, so this will be given as the voltage across these points. The current ISC is equal to the, we need to see that the voltage at this point to this point. Okay, voltage across the A and B, I can assume this is the point A and this is the point B. That means the voltage across the nodes A and B. So voltage across the A and B is nothing but, okay, so there is a across voltage across shunt field winding, shunt field winding is this one here, EB plus IARA is EB plus IA RA plus V drop. This is also equal to this one from this equation. EB plus IRA. This is also equal to your terminal voltage V minus IL into RSE. IL into RSE. Okay. So with this, I can write ISH as, is it clearer కనిపిస్తుందా మీకు?
Yes, sir.
Okay, I am writing at the top of the slide here. The value of ISH is equal to this is the voltage drop across the field winding divided by resistance, and therefore this should be equal to EB plus IARA కనిపిస్తుందా మీకు ప్లస్ VB. నేను పైన రాస్తున్నాను. Can you see this?
Yes, sir. Convertible.
Divided by RSH. So this is also equal to our terminal voltage V minus IL into RSE divided by RSH. So this is the value of the shunt field current which is passing through the short shunt compound motor. Okay. So by using these voltage and current relationships, you can solve any type of problem, depends on the voltages and currents. Okay. Is it clear?
Yes, sir.
So shall I move to next slide?
Yes, sir.
Now, next let us see the torque equations of all the motors. So already we have derived the torque equation as, is the torque equation what we have derived in the last class. The torque developed in any machine is equal to T is equal to 0.159 into 5 into IA into this one as Z P divided by A. Okay, so this was the equation which we derived in the last class for any DC motor. Am I right? Now, so from this relation, we can say that the torque produced by a motor will always be proportional to the air gap flux phi and the current flowing through the armature winding IA. That means that the torque is proportional to the phi into IA. Torque is proportional to phi into IA. And the flux is produced by the field winding or field current. Hence, phi will be always proportional to the field current. That is, phi is proportional to the field current. And hence, the torque developed by a DC motor is proportional to the armature current into field current. The torque is proportional to armature current and the field current. So now, for various types of DC motors, we'll see how this torque will be varies. Okay, so the torque variation will be depends on field current. So types of generators are classified depends on the field current, and therefore this field current will be different for different motors. So as per that field current, your torque equation will be varies. Okay, we will see that how this torque will be varying with field current. Okay, so now let us consider the DC shunt motor. So for DC shunt motor, we know that field current, I field, the current passing through the field winding is equal to V by RSH, and we know that it is always a constant. Okay, so I field is constant, and therefore the flux is also a constant because your torque is proportional to the flux into IA, or this is also proportional to IA into I field. Okay, and for the shunt motor, this field current is constant. This field current is constant, and therefore the torque which is developed will be proportional to only the armature current. Therefore, the torque is proportional to only the armature current. Hence, the DC motor torque is proportional to the only armature current. Just we have to remember this. In a DC motor, the torque proportional to only armature current in DC shunt motors. Okay, and now, and for the second case for the DC series motor, for the DC series motor, your flux is proportional to the armature current. So your the flux is proportional to the armature current. Okay, IA, and therefore here I field this is equal to I field is equal to IA, and therefore the torque is proportional to IA square. This is the square of the current. Okay, so the torque produced in a series motor is proportional to the square of the armature current. Square of the armature current. Okay, and now here I am not discussing about the compound motors here because the compound motors will have the flux in compound motors. Compound motor is nothing but it is having a shunt field winding plus series field. So the torque which is developed will be depends on which type of field winding is dominating in a compound generators. We will have that type of characteristics. Okay, so if The compound motor is having shunt field is dominating, and the characteristics of that motor is same as the shunt field motor. Okay, so here also the torque developed will be proportional to the shunt field. So it is a constant, and you can have a torque is proportional to Ia only. Okay, so it depends on your the field winding which is dominating in a particular machine. So that's why here we are not going through the in detail about this compound motors. Okay, now coming to the speed equations. Now, as we know that the back EMF which is developed in a DC machine is given by EB, which is equal to NP into 5 Z by 60A. So in this equation, your P is a constant. There are number of poles, always constant for a given machine, and Z is also a constant, and 60 is constant, and A is constant. Okay, so these all are constant. Only the variable parameters are the flux and the speed, and the remaining parameters Z P divided by 60A. This is a constant parameter. Only the variable parameters are the flux and speed, and therefore your back EMF which is developed in a machine is proportional to the flux and speed. And therefore now you can, if you want to find the speed, okay, so speed is now given as n is proportional to EB divided by 5. EB divided by 5. That means the back EMF, it is directly proportional to the back EMF, and it is inversely proportional to the flux which is developed by that particular motor. Okay, and this proportionality constant is K, which is given as 60 into A divided by this one, Z into P. Okay, so here the proportionality constant K is nothing but 60 A divided by Z into P. So this is your constant. And now here we are neglecting the brush contact drop. Okay, so V is equal to EB plus IA RA. Your terminal voltage V is equal to EB plus IA RA, and therefore EB is equal to V, the terminal voltage or supply voltage, V minus IA RA. EB is equal to V minus IA RA. This is the equation number 7. Now just we substitute this EB in your proportionality constant equation 5. So this will give you N is proportional to V minus IARA divided by 5. Okay. So here the flux phi is proportional to the field current. You can write the your speed equation as this. N is proportional to the V minus IARA. So here N is proportional to V minus IARA divided by I field. This is the speed equation. Okay. So in this, if I want to control the speed, either I need to control the voltage, the first one, okay, armature voltage, armature voltage. If I vary this armature voltage, then you can control the speed, keeping all the parameters constant. Okay, and the second one is you can change the resistance. Okay, this is called the armature resistance. Armature resistance, you can change it. So if you change this, the difference will be varying and your speed varies. And third one is field flux. You can vary the field flux control. So these are the three speed control techniques, speed control methods. We will discuss in detail about these speed control methods. Okay, so with the help of this speed and with a relation of V minus IA RA. Okay, so by controlling the armature voltage, you can control the speed of the motor. Okay, and with the help of your armature resistance, also you can control the speed, and with the help of the field flux, also you can control the speed of a machine. Now, so here with the help of this speed equation, n is proportional to V minus IA RA. Then we will discuss for the speed of shunt motor. Okay, so for the shunt motor, your IF is constant. The field current I, field current is constant. Okay, because and this is given by your terminal voltage V by RSH. Okay, and therefore your flux is also constant. So I can neglect this, and your speed equation can be represented as V minus IA RA. N is proportional to V minus IA RA. And similarly for the series motor, and in series motor, I field current is equal to IA. Okay, and therefore N is proportional to V minus IARA minus ISC into RS divided by IA. Okay, so this is a terminal voltage equation for the series motor. Okay, so with the help of any value, so your terminal voltage or your armature resistance and the combination of series field resistance, you can calculate the speed of a DC motor. Okay, so this is about the speed equations for shunt motors and series motors. And just take the speed regulation. Speed regulation. And the speed regulation is for a defined DC motor is defined as the ratio of speed regulation for a DC motor is defined as it is defined as the ratio of defined as the ratio of the change in speed corresponding to change in speed corresponding to no load and full load condition. No load and full load condition. 2. Speed corresponding to speed corresponding to full load corresponding to full load. Okay, and therefore percentage speed regulation. Therefore, the percentage speed regulation is equal to the speed under no load minus the speed at full load divided by the speed at full load condition into 100. So this is the formula to be used for calculating the speed regulation. Okay, so the speed regulation is obtained under loaded conditions for a machine. So how the speed is varying from no load condition to the full load condition. We have to check it out. Okay. And now we will discuss about. Is it clear now?
Yes, sir. Clear.
Yeah. Yeah. Now we will discuss about the characteristics of DC shunt motor. Okay. So for any machine, the performance of a DC machine or motor under various conditions can be obtained by the following characteristics. And first one is the torque and armature current characteristics. And second one is the speed versus armature current characteristics. And last one is the speed versus torque characteristics. So for any machine, that may be shunt motor or series motor or compound motor, the performance of these DC motors will be studied with the help of these three performance characteristics. Okay, one is the armature, torque and armature current characteristics. Second one is the speed and armature current characteristics. And third one is the speed versus torque characteristics. Okay, so we'll discuss about all these characteristics for all the machines one by one. So for torque and armature current characteristics. So here for the torque armature current characteristics, I need to draw these characteristics, torque versus armature current. Okay, so here I will take armature current on the x-axis and the torque on the y-axis. Okay, we need to draw the relationship for this torque versus armature current. And as we know that for a DC shunt motor, we know that the DC shunt motor, the torque equation, torque is proportional to normally phi into Ia. Okay, so torque is proportional to Ia. Okay, but normally the torque is proportional to phi into Ia, but for shunt motor, flux is constant and therefore the torque is proportional to only the armature current. Okay, so as torque is proportional to armature current, therefore now what must be the relationship between the torque and Ia? So it is a linear relationship, and therefore your characteristics will be like this. The torque characteristics will be like this. Okay, so this torque normally we can call it as a gross armature torque, which is developed. Okay, and under full load conditions, your torque will be like this. Okay, so here this will be the another torque, or you can call it as a shaft torque, TSH. Okay, for a current of Ia naught. Under no load condition, our machine is drawing a small amount of a current. Okay, under no load condition also your motor is drawing small amount of current. Okay, and shaft torque is going to be 0, but it is having a certain amount of torque which is known as lost torque. Okay, So we are representing this one as like this, okay, for a small amount of current, and this is having a TA naught, okay, or this is equal to TF, okay, where TF is called as the lost torque. Already we have discussed there are three different torques. This is the armature torque, TF is the lost torque, and TSH is the shaft torque. Now here this green line indicating that this is your net armature torque which is developed in a DC motor, and this blue line is nothing but the low torque or shaft torque. Okay, and this difference is nothing but your last torque. Okay, TF. Okay, TF. This is a loss torque. Okay, as we know that TA is equal to TF plus TSH. So at no load condition, armature draws a small current, which is nothing but IA naught. Because of this IA naught, which is developing a power, okay, P naught, which is equal to EB naught into IA naught. Okay, so this is nothing but the losses which has to compensate. So friction and windage losses plus shunt field losses, or you can consider this as a iron losses. So iron loss. Okay, so iron losses. Iron losses. So combinedly, we can call this as stray losses. These are called stray losses. Okay. Is it clear? So what are the torque versus armature current characteristics? So this one. So this is a torque versus armature current characteristics. So this is giving you the linear relationship. So this is also a line, but it is not passing. TSH is straight line, but it is not passing through the origin. But your gross torque TA will be uh, passing to the origin. Okay, so this is about the first characteristics. The first one, the torque versus armature current characteristics. And next, we will discuss about the speed versus armature current characteristics. So, as we know that this first shunt motor, the speed equation is given by, for the shunt motor, the speed equation is given as n is equal to V minus IARA, V minus IRA divided by 5. But flux is a constant parameter, and therefore this can be represented as n is proportional to V minus IARA, V minus IARA. Okay, and now I need to draw the characteristics here with respect to speed and current. Okay, so I need to draw the speed versus armature current characteristics. So this is your speed. Okay, so at no load, whenever your armature current is zero, at no load, at no load, your armature is not drawing any current, but speed, the machine is running at the rated value. The speed of a motor under no load condition is n0. It is almost equal to the rated value, and therefore at this point this is running at a no load speed of n0, and this will be given like this. So this is always constant. This is a no load speed. Okay, then as the load increases, as the load increases, then as a consequence your armature current increases. As a consequence here armature current increases, but we see that V is a constant parameter, your supply voltage is constant, and your armature resistance is also constant. And therefore, your speed N will be now proportional to V minus IA RA. As your IA is increasing, the net value, this drop, IA RA drop increases, but the net voltage, net speed will be, the difference will be gets decreased. The net value will be decreased. That means the speed of a machine, the speed decreases. Okay, as this armature drop is very small, this is a very small, and therefore, but the drop in the speed is also very less. Drop in speed is very less, and therefore you can observe that the drop in speed, this is called as a drop in speed here, this will be like this. Okay, so this one is a constant speed line. Okay, and this is a green line is a drop in speed. Okay, so this drop is very small, this drop is very small because your armature resistance is very less. Okay, so this drop, this is a drop is small as armature resistance Ra is small. So this is speed versus armature current characteristics. Okay, speed versus armature current characteristics. Next, last one, the torque versus speed characteristics. Okay, so in the speed torque versus, okay, the speed and torque. As the torque on the machine is increases. Okay, so here at no load condition, the torque produced by the motor is TA naught. At no load condition, the torque produced by the motor is TA naught, and the motor rotates at a no load speed of N naught. Okay, this one. This is the speed N naught. Now, as the load increases, the torque requirement is also increases. So, to generate the required amount of torque, the motor has to draw more armature current. Okay, so as the load increases, torque requirement also increases. So to generate the required amount of torque, the motor has to draw more current. That means your IA must be increased. Okay, and therefore, as the armature current increases, as from our previous equation, the same equation, V is proportional to N is proportional to V minus IA RA. So as the torque is increasing means your armature current is increasing. So this IA RA drop is increasing and the net speed will be gets decreased. Okay. So therefore as the load increases, torque will also increase and the speed decreases. And the speed decreases. Okay. So this speed is not a significant, not significant because the resistance is very small. So this drop is small. The drop in speed is small as the armature resistance is very small, and that's why these motors are called as a constant speed motor. The DC motor is called as a constant speed motor because the drop in speed is very, very small as the load increases on the particular motor. Okay, so this is about the characteristics of the DC shunt motor. Okay, so I will stop here. So tomorrow we will discuss about the characteristics of series motors, compound motors, and applications.
Yes.
Okay. So anybody, if you have any doubts, you can stay for 2 minutes and you can ask me. I will answer your questions.